deep learning in the context of tomographic reconstruction. And as you see already, this is, first of all, let me say that this is a joint work with Gita Kütinyok, who is in München, her PhD student Hector, who is in Berlin, and Philipp Petersen, who is in Vienna. And as you can make out already from the title, it's going to mix quite a lot of different topics of mathematics. So the presentation will be a bit fragmented. I've been really trying to put a red thread through the whole thing, but let's see how successful I am at doing that. So first, some motivation behind the whole thing. I mean, tomography is essentially about recovering the interior structure of an object by exposing it to some kind of radiation from different directions. And the typical example being hospitals, of course, where the interior structure is anatomy of the patient. But you can also use tomography in many different circumstances. And for example, industrial usages, you typically have like a conveyor belt or something like that, where objects are passing by with a fairly high speed. And for that reason, you don't have the time or the facilities to gather the necessary data that you would like to. So this typically leads to what is called limited angle data. That means that you're radiating from not sufficiently many directions or not evenly distributed directions around the object. The objects may be also large so that you cannot essentially or partially opaque, which leads to what we call the region of interest data. And the same also applies to, for example, non-destructive testing. In this case, for example, they are scanning these are rockets that are, these are actually nuclear missiles that are supposed to be ready to be sent away. And then you want to, from time on, you want to make sure that they don't deteriorate when they are kept in storage. So you do this type of tomographic scanning. And this is typically where the object is far larger than the field of view, and then you get what is called region of interest data. And perhaps a more peaceful application is when you have molecular structures in ice, embedded in ice, and then you radiate them with electrons. So from the point of view of the microscope, this is an infinitely large slab, plane parallel slab. And in there are a bunch of molecules, and then you're rotating this whole slab, and you get typically what we call the limited data plus region of interest data in that context. So all of these applications lead to this type of limited data problems in tomography. And to make a long story short, if you pre-process data in these applications that I was just mentioning, you could interpret them as the ray transform, which is written here. So the F here is a function that you somehow want to recover. It's representing the interior structure you're interested in. And then A of F is an integral transform, essentially taking the line integrals of this function. And the family of lines that you're measuring on is the acquisition geometry, and your data can be interpreted as noisy samples of the sky. So this is a very super fast introduction to the mathematics of tomography. And limited data issues that I was mentioning, I was essentially name dropping, mentioning region of interest, I was mentioning limited angle. What the implication of these limitations to the acquisition geometry is that when you typically have limited angle, you typically end up with an inverse problem that is severely opposed. The notion of inverse problem here means that you want to invert the operator A. You want to compute, it's a regularized inverse to it. And you can actually determine geometric criteria for this manifold of lines so that you don't get this. And in the case of parallel beam data, it's called the Orlov condition. For cone beam data, where the radiation is a point source, and it's essentially like a cone beam exposure, is called the Thuys condition. When these conditions are not fulfilled, you end up with a severely ill-posed problem. And for region of interest, you even have problems where you have formal non-uniqueness. So for that reason, limited data tomography is something that you really try to avoid end up in. So if you can engineer your way out of it, you really do that. But in these examples I was showing you, there is no easy way for you to engineer your way out of these limited data issues. Okay. Okay, interesting. So let's leave aside tomography now for the time being and turn our attention to deep learning and inverse problems. So I guess I just saw the names on the audience, so I think all of you know what an inverse problem is. So I'm going to skip this part and directly move to the mathematical formalization. So the most classical way of formalizing an inverse problem is to phrase it as an operator equation, where A is the forward operator. In tomography, it was typically the ray transform, this integral operator. And F star is this image or this function that you want to recover. And data is then a sample. You can see it as a random sample of some random variable G, where you have this additive observation error. You might view this deterministically. You don't care about the statistical properties, then you're definitely in the function analytic viewpoint. Or you might still try to account a bit for the statistical properties of this observation noise. In that case, you will still adopt the frequentist viewpoint. And of course, there are many possible solutions to this inverse problem, in particular if you're undersampling the data. So, and also in the context of uncertainty quantification, where you talk about uncertainties in the recovered estimates, you would like to be able to recover perhaps a probability distribution of I call this model parameter, think of it as an image. So quite often it makes sense to view not only the data as a random sample, but also the ground truth image, which is here seen deterministic, as a random sample. So for that person, if you introduce that viewpoint, then you essentially change the formulation of the inverse problem. You are now not necessarily looking for a solution, but more for this posterior distribution of solutions. That's what you're doing. And in this context, you have a prior distribution, a probability distribution, which among others generates the ground truth image. So data is suddenly a sample of a conditional random variable, namely the random variable generating data, assuming conditioned on the ground truth unknown image. And you still have the same essentially model for how data is being generated, but here we are now putting in a random variable instead. And the F star is still the unknown ground truth image. And then ideally, we would like to recover the posterior distribution. Now, this all sounds nice. And of course, you can apply Bayes' theorem and express the posterior in terms of the data likelihood and the prior. And there has been quite a beautiful, I would say, mathematical theory developed that investigates how this posterior distribution behaves asymptotically as this observation error tends to zero. So there's some quite nice theory that's been developed, both for nonlinear forward operators as well as for linear. But I'm not going to go into that. That's a separate, several series of seminars you can easily hold about that. I'm going to target the issue of how practical difficulties in using this viewpoint. Because if you're going to do 3D tomography, for example, just to give you a feeling, even though we discretize the data and the image, they are typically high-dimensional arrays. So if in a 3D medical imaging setting, for example, the F here, which is innocent looking, is easily about 130 million dimensional. And in medical setting, where you typically oversample, data is easily 800 million dimensional. So talking about recovering posteriors in that context is totally out of the question, just because of sheer size of the problem. So for that reason, it's too complex. So what can you do? Well, you need to settle for something less. So either you cover a suitable estimator that summarizes the posterior in a suitable manner, it could be posterior mean, for example, or you generate samples. And here I want to say something. When I say recovering an estimator is not a reconstruction. It's a reconstruction method. That's a very, very subtle difference, right? So when we have an estimator at our hand, it's a reconstruction operator by itself. So I'm going to transition now and say that the idea is to use deep learning to actually learn a suitable estimator from training data. So again, I'm rephrasing the problem here. I'm going fast because I have a lot of material to cover. Sorry, guys. So the inverse problem now is to recover a suitable estimator of this conditional random variable. And the same, we still have the data as before. And of course, then you can ask the question, which estimator am I supposed to recover? And if you're going to learn this from training data, then that is kind of determined by the type of training data you have access to and the way that you phrase your learning problem, okay? And then the computational aspect is how am I supposed to do all this learning aspect? Then that's where the neural networks, deep learning comes into the game. So progressing quickly, just to give you a feeling, if you have typically, we're actually going to work with the first line here. I'm not going to do the other ones. So if you have paired data in tomography, it means you have a bunch of pairs. You have images, 2D or 3D images, and corresponding data, elements in Y, which is tomographic data. Of course, these are high-dimensional arrays, but nevertheless, you have a bunch of these pairs of that type. Then you could essentially use machine learning or deep learning to approximate Bayes estimators, which in particular include, for example, the posterior mean. So how do we do that? So if our task is now to recover a Bayes estimator, I'm going to explain what a Bayes estimator is in a second. So the task is now to recover a Bayes estimator. And we're going to learn this, right? So instead of trying to handcraft the prior for F and using the data likelihood, we say, okay, we put that all aside. And we say we have a bunch of training data, a bunch of samples, Fi and Gi. Each of these are 2D, 3D images and corresponding tomographic data. And we assume they are random draws from this random variable. And so essentially we have this type of relation. There's noise also, so there are noisy realizations here. And the Bayes estimator is defined in the following way. You're looking at all possible reconstruction methods. So each R here is a reconstruction method. It maps data into images, Y into X. And for each choice of reconstruction method, you have a loss function. You can assess how good it does in terms of a certain distance, or it doesn't have to be metric, but there's a loss function. And then you're taking the expectation over all possible realizations of images and corresponding tomographic data. So you're looking at the reconstruction method, which on average performs the best, minimizes the average error. And that's a Bayes estimator for you in a nutshell. Now, obviously, this expectation is something pretty dramatic thing to even try to compute. And you don't even know this joint measure. You have no idea what the joint measure is, because for you to know this, you would need to know the prior, that F is distribution of F. And we don't want to handcraft a prior here. So instead, this is where you resort to your training data. You say that these guys were random draws from this distribution mu. So I'm just simply replacing this unknown probability measure by its empirical counterpart given from this training data, essentially meaning that we're replacing this expectation by this empirical minimization. Then I'm saying that minimizing over all possible measurable mappings from Y to X is something that is too complicated, obviously. So I have some kind of a finite dimensional family of reconstruction operators. So I'm instead replacing this infinite dimensional optimization with a finite dimensional one. And these are the two steps I'm doing. And then I'm replacing this infeasible learning problem with this empirical counterpart. And this is a standard supervised learning problem in machine learning. Now you would say, what the heck, if I just put a generic deep neural network here, it's not going to be a feasible approach. Clearly, if you took this 3D tomographic imaging example that I was showcasing a couple of slides ago, this means you would learn something of the order of 10 to the power 16 parameters, and the amount of training data you need for that is just totally out of the question. So there's no way for you to do that. So a critical element here is to choose an architecture of a deep neural network, which means you're choosing a very specific parameterization, which is adapted to the inverse problem in the context. In particular, we're choosing a parameterization that includes the prior knowledge that we know that our theta should have an inverse, which is essentially A. And A is the one that we know, right? But there's no point for us to learn A. We can handcraft A. We know A is the ray transform in this example. And we also know it's adjoint, which is the back projection operator. So this can be done with a suitable network. I'm not going to go into this. I'm just saying that it could be done. The second part is, of course, which loss function should I pick? And that brings us to essentially the task-adapted philosophy. So we don't do imaging for fun. We do it there's always typically a post-processing task that takes place afterwards, once you've done your image. And this is typically what is done for decision-making. So there has been a trend, I would say, in certain parts of inverse problems to see if you can do things jointly. So you want to do the reconstruction jointly with a certain task, like segmentation, for example. So the question is, if you go back now, I was just arguing how you can see reconstruction as a Bayes estimator, essentially minimizing this average error. You're picking the reconstruction method that is essentially minimizes the average error. And here you have a loss function. The question now is how to pick the loss function. You could take the squared 2 norm as a loss. It's a very, generic choice. And actually, in that case, you would be essentially approximating the posterior mean. But you can pick also more fancy losses that are more, you can look at what computer vision guys are doing. And what I'm going to do is to try to adapt the loss to a certain task that's going to take place afterwards. So what do I mean by that? What do I mean by adapting it to a task? So assuming you have a reconstruction again, represented by R theta, it maps data into image space. And this guy is given by Bayes estimator, right? There is a bunch of statistical theory behind this, but sure, there is something that you can learn from training data. Now, assuming you have a task also, in this case, represented by segmentation, which it can also be phrased as a Bayes estimator. It's not reconstruction, but it's still a task, right? It maps an image into something else, an element in some decision space. So if this is also represented by a Bayes estimator, then typically you can, not only can you do the composition here between these two guys, you can also suddenly retrain the composition. And let me say, I need to keep an eye on the time. So essentially you have a loss function for the reconstruction, which is done for how to train the reconstruction operator. You have a loss function for the task, for example, for the segmentation, which comes into the game for defining the task operator, which is essentially doing a segmentation, for example. So the sequential training will be that you do the best you can to train the Bayes estimator for reconstruction. And then when you train the task, you use the train Bayes estimator for reconstruction as a fixed operator here, and you just train for the task. That's a sequential pipeline. But you could also do what we call end-to-end. You could do the composition here, which is the composition. These are 2 Bayes estimators here, one for the task and one for reconstruction. And then you do the joint training while minimizing the loss for the task, which makes sense, right? Ultimately, you're interested in the task at the end of the day. Or you can do a convex combination where you mix the loss functions for the reconstruction with the loss function for the task, and you do the joint training. And this is what we call task-adapted reconstruction or task-adapted training. So I'm going to come back to this later. So I'm going to ask you guys to put this aside a bit. I'm going to bypass this example and just want to mention something. So an advantage of using Bayes estimate, phrasing a reconstruction method in terms of a Bayes estimator, an advantage that comes with doing that is that you have the flexibility to also couple a post-processing task, which is given by a Bayes estimator itself. So it opens up for doing things jointly in a very nice canonical way. So we'll come back to that. So I'm going to now switch gears to a third topic, which is microlocal analysis. So we've mentioned about motivation. We've done a bit decision theory. We phrased reconstruction in a decision theoretical framework. I try to motivate the users of Bayes estimators in that context. So we put that aside and let's turn our attention to microlocal analysis. So singularities carry important information. In particular for images, singularities would intuitively translate into edges. And there's all kinds of biological evidence that the way humans or even mammals in general perceive visual information, there is actually biological evidence that edges is a critical component in that. Now, leaving aside the biological and let's say application motivation, also from the mathematics point of view, singularities are of interest. So already in the 70s, people were interested in, let's say, how would singularities propagate when you typically solve PDEs, for example. And there it turns out that to be able to understand that, it's not possible to just study where the singularities are located, which means that it's not enough to know the singular support. So Hermander introduced the notion of Wavefront Set, I think in 71, which is a way of extending what additional information do you need to be able to have a chance of describing how singularities are transformed when you operate on them with a certain class of operators. So what is then the Wavefront set? Of course, I see that half of the audience already knows this, but nevertheless, let's go through this. From a very practical point of view, edges or singularities are, if you take imaging in the let's say, images, if you think about images, it will be somehow regions or boundaries where the intensity is making a rapid shift. Mathematically, of course, you can think of the Fourier characterization of smoothness. If you represent an image by a real valued function, then we know that it's smooth if and only if the Fourier transform decays rapidly at infinity in all kinds of directions. Now I got a warning that my connection was unstable, but I'm continuing. Now, obviously, you can multiply this function by a cutoff function locally around the point, and you can study the Fourier transform of that cutoff function, and that will essentially give you a characterization of the singular support. But you can also study which frequencies in the frequency space that is causing the singularity, because obviously, if it's not smooth, there will be some directions where you don't have this rapid decay. And this is the microlocalization, essentially, and this brings us to the formal definition of the wavefront sets. So here it's stated for the general case where we have a function on a manifold. So we say that the function is smooth, microlocally near a point in a certain direction in quotation marks, if there is a cutoff function, first of all, near that point, and that the Fourier transform of that localized function decays rapidly in some conical neighborhood of that direction. And if that's not true along that direction, then you say that this pair, x and psi, belongs to the wavefront sets. Now, if you're going to be a bit picky about this, you have to see that this is a cotangent space, and it's a bit tricky, and that's because this is a manifold. So, of course, a simple example is if this manifold is Rn, then you can identify this direction with a directional vector in Rn itself. So moving ahead quite quickly, just to illustrate this a bit more easily, to digest this definition, assume this function is smooth everywhere except for a hypersurface K. And then clearly the singular support is this curve K here. And then if you have a point here, the directions that are in the wavefront set are those that are co-normal to the surface here. And there's actually, I think there's a nice physical intuition to this. If you would imagine K is a wall and you'll be driving a car and you want to say, how do I feel the wall the hardest? If I'm just touching it tangentially, I wouldn't feel it. If I drive into it straight ahead along the normal direction, then I definitely will feel that singularity or the wall there. So in that sense, it's a kind of trying to put it in a more physical, intuitive setting. So essentially the wavefront set would be the point X and these two co-normals, so to say. Okay, and this is just the same remark that be careful that psi is actually not an element in the same space as X. Especially, that's definitely not the case when you're dealing with a manifold here, but okay. Now, this is all nice and beautiful. So what's this history about in tomography then? So I would say people were starting to look at the radon transform as an operator and analyzing it from the microlocal point of view, that is trying to understand what the radon transform does to wavefront sets. It can be traced back to work by Gilliman and Sternberg. If I'm wrong about the history, please help me out here. In parallel, I would say there's a notion of lambda tomography, which is saying that let's try to recover not necessarily the function, but some other function whose wavefront set is more or less the same as the function we're interested in. Can we do that let's say, in a filter back projection style way? That's lambda tomography. And I believe it was done independently of, there was initial attempts in this direction, was not tying it to microlocal theory, but then obviously later on the connection was clear. And then of course, from the end of 80s and beginning of 90s, this whole thing took off. There were a number of seminal papers by Ozan and Greenleaf about extending this microlocal analysis to various variants of ray transforms. And then this has taken off, and then people have done this for also other type of operators that are popping up in imaging, like in radar and so on. There's a lot of work in that direction. Bowman and Quinto also used this type of theory to prove support theorems, and Todd Quinto also looked at certain limited data problems already in the early 90s. And this is, of course, all to be able to see essentially how to relate singularities in tomographic data to singularities in the image that you want to recover. That's the baseline question. Now, if you go tie back to this limited data problems, I was mentioning in the very beginning that there are limited data problems, and the price you pay when you transition, when you are working with limited data tomography, is that you not only might lose uniqueness, but formal uniqueness even, but you definitely lose stability. You pay a price in stability. Well, if you lessen the question, if you say, I don't necessarily have to recover the function, I'm happy with its wavefront set, then you might actually gain. So there's a theorem that is characterizing the visible singularities. You can do that purely from the geometry of the measurement manifold. Essentially is that if you're talking about the ray transform now, the G, which is, I call it the data now, is a function on a manifold of lines, keep that in mind, whereas F is a function on the plane or in space. And if there is a line in the manifold that goes through the point X and which has psi as a co-normal, then that point would also belong to the wave. That means, and that point belongs to the wavefront set of F, then it will make a footprint also in the data. It's recoverable, it's visible. And not only that, the recovery is actually mildly opposed. So even in the limited data case, there is some technical exceptions here, which I'm bypassing. The recovery is essentially as ill-posed as regular filter by projection in a fully sampled data setting. So you can actually do this recovery using standard techniques from sampling theory. And of course, how does this translate in the case when the function has a jump discontinuity at a hypersurface K? Well, a singularity that is a point on K is visible if there is a line in my measurement manifold that goes through that point and is tangent to this surface. So this is the nice, let's say, characterization of the visible singularities. And then there is the notion of canonical relation, of course, is a well-known thing in microlocal theory. It's an explicit mapping that can relate the visible singularities to the restricted, when you restrict the wavefront, the ray transform to this measurement manifold, M, and you can look at the wavefront set there. You can go in between them if you can work out this canonical relation, and this, of course, depends on which operator you have. So we'll come back to these things rather soon here. So this is the theoretical part, and of course this is quite exciting, and this is a bit tempting to say that could I use this computationally? And this brings us now, we're going to get closer to putting the pieces together. So if I want to do this computationally, the first challenge I'm facing is that my function is, of course, I never have a function, right? I have a digitized image typically. So I might say my function is given, my image is given in terms of pixels or voxel values. And then the wavefront set is supposed to be the singularity, is a more richer description of the singularity. So typically it would be, if I could recover the wavefront set or extract the wavefront set from such a digitized image, it will amount to, or it will definitely contain the edges. So why don't I take a look at what computer vision people have been doing when it comes to edge extractor or edge detectors. There's a rich field that is just dealing with various types of edge detectors. Well, most of it is semi-heuristic and it typically fails in this context. So clearly, this is already an indication that maybe representing images by pixels or voxels is not the best way to go about this problem. So then you might look at computational harmonic analysis. There's a rich theory about certain multi-scale directional representations. There's a real ditch, curvelets, contourlets, and goes on. They are, they are not only about edges, but they're also about textures, but they typically contain this directional information. And for some of these, you can actually relate the way, you can actually express the wavefront sets in terms of these representations. But the wavefront set is an asymptotic notion. It requires you to assess the decay of the Fourier transform in certain directions, right? So it essentially amounts to that you would need infinitely many of these coefficients in these representations to be able to assess it, whether you are in the wavefront set or not. So there's also a computational issue. So the idea popped up about 2 years ago when we were discussing this with Gitta in Berlin. We were having a meeting with her, and then maybe we can use some kind of a neural network classifier. Maybe try to learn this thing, right? It was a very very vaguely defined idea at that time. So here you need to try to make precise what you mean by a wavefront set extractor. That's what we want. I'm going to give you a function, ideally a function represented in some, let's say, suitable representation. And the task is somehow to extract the digital counterpart of the wavefront set. So what do we really mean by that? I think it's worth spending a couple of seconds on what you would like to have, properties you would like to have from such a wavefront set extractor. So you can look at band-limited functions. I mean, things that have a bounded or a compactly supported Fourier transform. So obviously they are, and the Paley-Winnie theorem will tell you that you can essentially, you need to determine these by appropriate sample data. Then you can talk about the wavefront set extractor which is essentially mapping this thing. It takes such a function, it will map it into a subset I have now done this identifications. It's not the manifold anymore, functions are on Rn. And here's now the idea. If I take a function L2 and I project it to this band-limited space, and I apply this wavefront set extractor, and I compare that against the wavefront set of the function, I somehow, and I let now the band limit go to infinity, I would ideally want these two as sets, the distance, sets-wise distance, to somehow go to 0. That would be very desirable. Well, it kind of turns out that that's not possible. There is no such up mapping with these properties. So this also indicates that maybe we should take a different viewpoint of what we mean by extracting the wavefront sets. And anyway, if you anyway want to do machine learning in this context, that also points to that you need to maybe phrase this as a statistical estimation problem. So what I'm going to do next is that I'm going to try to phrase the wavefront set extraction task as a task of statistical estimation. If I can do that, and then I could maybe see the wavefront set extractor itself as a base estimator, and then I have a essentially ready-made conceptual machinery to say, oh, I can maybe address this by deep learning. So that's roughly the idea. So returning back to statistical decision theory, in a very abstract setting, decision theory is dealing with, there's some tasks, an abstract task, which is represented as a mapping from some model space V into some decision space D. Then there is a feature space, I call it feature space. It's a family of probability measures on the model space that are parameterized by this feature space. We'll come back to that in a second to what this is going to be in our context. So right now I'm just, putting this down abstractly. And there is also a loss function for the decision, so for elements in the decision space. And then there's this mysterious kappa mapping. We'll come back to that in a second. So first of all, a base estimator. And now you might recognize you might recognize a couple of slides ago that when I was phrasing reconstruction as a base estimator, it was very similar. So we are looking at all possible operators, decision rules, that maps a model, an element in model space into the element in decision space. And among those measurable, the M here stands for measurable mappings. Among those, I'm picking the one that is minimizing the average error. This is the averaging component here. The average error in terms of the loss function on decision space. Okay, this is very abstract here. And of course, I need this joint probability measure and so on, very similar to what we had with reconstruction. And the deep learning counterpart is to say that we don't have access to this measure mu, but we have training data generated by this, again, by this joint law. And then we can replace this expectation by the empirical counterpart. And then we replace this all possible measurable mappings with this parameterized family, okay? So this is exactly the same way we handled reconstruction. There's no difference, conceptually no difference. It's just that we have an abstract task now. So let's see now, by choosing V and D and LD and so on appropriately, we're going to squeeze in the notion of wavefront set extraction into this formalism. So the task now is to extract the wavefront set of some function. And in this context, it's going to be given in terms of its Sharelett coefficients. So we might see the model space here. At each point in some domain omega, we have a bunch of Sharelett coefficients, right? And that's going to depend on how many scalings and sharings you think and so on. But nevertheless, there's finitely many coefficients at each point in this domain omega, okay? So we can see our model space as a mappings from omega into this RC. That's a way of encoding the Sharelett representation of an image. Well, that was the model space. What about this feature space, this mysterious set that we use to parameterize some probability measures on, right? What is that in our context? Well, elements in the feature space will be digital wavefront sets, or digitized or digital or discrete. Okay, what do I mean by that? Well, what I'm doing is that I'm taking, essentially I'm doing already a discretization of the cotangent direction. So I'm essentially tessellating the sphere. And I'm associating to each point in this domain omega where the image is living, I'm associating M binary labels, okay? And each of these guys have the value 0, 1, right? So if it's 1, then it means there is a direction that's contained in this fixed tessellation, such that x, psi is a part of the wavefront set of the function. That's the interpretation of the label having the value 1. Otherwise, it's 0. So if the function is smooth at x, then of course you will have all these labels will be 0, right? So, and then I would say, okay, but this is done pointwise. At each omega, I have these M binary labels. So if I'm going to have a set of these, I could as well see elements in this feature space as mappings from X into these labels. Each of these labels was 0, 1. So I could see the feature space as measurable mappings from omega into the 0, 1, M of these, because I have M of these. M comes from this the way I'm discretizing these directions, okay? So this is my attempt at essentially putting a digital wavefront set. Yeah, in some sense it corresponds to, intuitively at least, to digital wavefront sets. But now, remember, there was, I mean, the whole concept of trying to find one such wavefront set was a bit futile because of this lack of clairvoyance. So the decision space is actually not an element here. It's a probability measure on these things, right? So it's essentially a point-wise, I'm mapping at each point in omega in the image space where the image is supported. I'm looking at the probability measure over these binary labels. This is my decision space. So it's essentially a probability measure over possible digital wavefront sets. That is my attempt at shoehorning this wavefront set extraction problem into a statistical decision problem. And of course, a probability measure over 0, 1, it can be replaced by a number between 0 and 1. So essentially, the decision space is measurable mappings from omega into 0, 1, M of these, 1 for each label, right? So, wrapping up things here. So the statistical model was, this is our model space. These are the Sharelett representations of the images. This is my curious, let's say, parameterization of this is my feature space, but these are my digital wavefront sets. And then the decision space, the one that I'm going to work with, is actually probabilities on these digital wavefront sets. So they can be represented by measurable mappings from omega into 0, 1 instead. And the feature map is just to put the Dirac mass on a certain digital wavefront set. So what is the loss function then? What do I mean by, and of course, now remember, elements in D are probability distributions over wavefront sets, right? So I need to have a notion of a distance between probability distributions. And one typical one is to take the cross entropy. It's a classification problem essentially here. So I have M of these because it's an M-fold, it's for each direction, right? A discretized conical direction. So I'm taking the sum of these guys, and these are pointwise for each omega here, right? So I'm integrating over omega. So I'm essentially integrating sum of M pointwise cross entropies that are measuring the distance. Okay, I'm saying these things fast, and I know there's a lot to digest, but yeah, I'm also squeezed for time, so I'm pushing forward here. So now we have all the elements, and of course, then now I can do some abstract hand waving. I say, okay, we can learn if we have pairs ZI, which are digital wavefront sets and corresponding sharelet images. If I have pairs of that type, I can then do the deep learning philosophy here, replacing this expectation by the empirical one and so on. But then what is the parameterization I'm going to use, which is adapted for this domain? Well, that's going to turn out to be, I'm going to call it density. I have no time to go through that. It is a deep neural network which is specifically adapted for this purpose, for this task of recovering this type of probability distribution of wavefront sets. I'm just simply have to do some hand waving and refer to the peer-reviewed papers that are describing this. But the important part is, let's see how this thing performs a bit, with lighting this up a bit. So here's a ground truth image to the left. So keep in mind the following now. So what this density here is a deep neural network that as input takes a sharelet representation of an image, and as output provides you a probability distribution over digital wavefront sets. That's the output of the neural network. And then I could maybe pick just the most likely or something like that. I need to pick one candidate. I could just do thresholding or something like that. Okay, so here's the ground truth image, and this is what density would output. Now the coloring here on the edges is to encode the directional information. So remember, it's supposed to be somehow the wavefront set, right? So it's not only where the edge is located, it's also which direction the edge is somehow pointing to, right? And if you look at the ground truth edges, that's what you would get. You'll see that the method is suffering where you have intersection. That the white is that there are more directions. That's what it means. You could also look at the ground truth image where you have a ramp type of thing, not a jump discontinuity, but more like a ramp type of regularity. And here is what density would perform in that context. And this is what you would be somehow the corresponding ground truth image or edge sets. So this is to show you that you can also handle different type of singularities, not only jump singularities. You could also look at a more natural image, like a photograph here. And if you apply the density here, this is what it would produce to you. And then you might look at what is somehow the ground truth edges here. Well, this is human annotated, so it's a good question. Is this the ground truth? I mean, a human has chosen to not working out all the small edges that you might have in this part. But nevertheless, this is essentially to give you a feeling. And the final part is, of course, to show you guys that it also can deal with a mixture of ramp and sharp singularities, and not the less also on manifolds. I was mentioning that when you work on manifolds, you have to be a bit more careful because your wavefront set, these so-called directions are cotangent vectors. And in this case, we have used the deep neural network to extract out the edges of the sinogram, which is the data domain of the tomographic data. So here to the left, you have actually an image on lines in 2D. So it can be parameterized like that and shown in this manner. But this is just, all of this is about extracting the wavefront set, right? So if I'm happy, this would somehow give me a digital wavefront set from a image that's been represented by its sharelet coefficients. So I was mentioning a couple of slides ago about a situation where you have visible and invisible parts of the wavefront set. In that context, you need to talk about an inverse problem. So there's an operator in between, typically the forward operator. And we're talking about which parts of the wavefront set of a function that makes a footprint that becomes visible, in principle is visible in the data. That is, so depending on the forward operator, especially if A is a ray transform, you can actually work out, and the geometry of this manifold, you can split the wavefront set into a visible and an invisible component. I was mentioning that theorem a couple of slides ago, how to do that. Now we can show, and of course it's tangible. Could I use machine learning to in-paint the invisible portion here? It's a bit kind of tangible, right? I mean, is that even possible? And again, the model space now is the visible part of the wavefront set. It's the same construction with these binary labels. The only difference that I'm now putting a 1 here in the binary label if the direction is contained in the visible component here. So again, it will be measurable mappings from omega into 0, 1, but only for the visible components. And then the feature space, decision space, and feature maps are just as in the Wavefront Set Extraction setting. And then the loss function again is now is a Wash-Stein distance because we had a hard time making it work with the entropy, cross entropy. And then you can shoehorn this into a machine learning context. And then here is a UNet that is parameterizing the operators. So I'm running out of time pretty dramatically. So I need to, sorry guys, I'm going fast already, but I want to get to, yeah. So let's see what do we have now. I've been rushing through this and crossing a couple of mathematical fields that are not necessarily commonly treated at the same time. So I'm claiming that we have a kind of a machine learning based wavefront set extraction machinery here, okay? To some extent, we can apply a deep neural trained neural network to an image that's been given in terms of its Scherler coefficients, and it will output some kind of a probability distribution. It's kind of a classifier that tells you whether a point is belonging to a wavefront set with a certain direction. And you can threshold that to actually get a digital wavefront set. That's one component. Another component is that we have a reconstruction that was almost in the very beginning. I was phrasing how we can phrase reconstruction by itself, forget about wavefront set and deep microlocal theory, as a deep neural network. It's a nonlinear operator. Now, this is the part I'm totally bypassing here. I'm not mentioning it. It turns out that for certain deep neural networks, you can actually work out the canonical relation. This is a nonlinear operator here. So it's not really a common thing to work out the canonical relation, but at least for an approximative, you can do that. I'm claiming you can do that. Okay, and this will allow us, so this will somehow give us a canonical relation also for the reconstruction operator, which will allow us to take a wavefront set on the data domain and map it to a visible wavefront set in the image domain, in principle. Now I have this characterization of the visible and invisible components. And then the final portion in this puzzle is the in-painting component. So I was just phrasing it as a decision theory problem. So we have 3 deep neural networks here, okay? And to extraction, reconstruction plus the canonical relation, characterizing the visible parts that's a paper and pencil exercise, nothing with machine learning, and then the wavefront set in painting. So reconstruction part is so-called joint with the learn primal dual approach. So when I say the word joint learn primal dual, it's when I'm performing this part B and part D jointly. That's why I was mentioning this task adapted approach in the very beginning. Okay, so let me just conclude. I'm almost out of time with an example. So we're going to apply this machinery now, this quite intricate machinery, to limited angle parallel beam 2D CT. And we're going to do that. We're going to compare a couple of model-based methods, filter back projection, Tikhonov, regular Tikhonov, total variation, and a compressed sensing Scherler-based approach, sparsity-based philosophy. They have all been optimized. The regularization parameter in all these have been optimized with respect to minimizing the mean square error in the image domain. We're going to pitch these methods against a couple of deep learning based methods. I'm going to do the learn primal dual, which is essentially a Bayes estimator, which is not aware of the microlocal aspects at all, but it's been trained at least on limited angle data. So it's domain adapted in that sense by the choice of training data. It is aware of the forward operator and the adjoint of the forward operators. In that sense, it's aware of the inverse problem to some extent, but it's not aware of the microlocal aspects of the problem. PhantomNet is a paper that is a method that was done fairly recently by people in Lassas and Tatiana and Samuli and so on in Helsinki, where they are essentially trying to apply regularization only in the invisible components. So this is actually using the microlocal characterization of the visible and invisible singularities. And then it's the joint LPD, which is the entire pipeline I was mentioning to you slides ago. And we're going to run this for limited angle data, 40% missing wedge. We're going to first do it's going to be trained on random ellipsoids first, and then we apply that, the deep learning based methods. And then they're going to be applied on Shep-Logan type of objects. And then we're going to move on to more realistic phantom. Okay, so I'm essentially out of time, so just give me 1 more minute to just showcase you the performance. So to the upper left corner, you have the ground truth image. And this is what filter back projection and Tikhonov and TV and Shelets are doing for this from the limited angle. As to be expected, this is the missing region here, the 40%. So this is not to be surprised about. This is what the learn primal dual method is doing. So it's essentially a Bayes estimator. It's totally unaware of the microlocal aspects of the problem, but it's been trained on limited angle data. So in some sense, it's implicitly, slightly in that sense, aware of it. This is the performance of the phantom net, which is this, actually that's worse than the learn primal dual. And this is the joint learn primal dual. So to show it a bit bigger, so this is the ground truth. This is the Bayes estimator, which is unaware of the microlocal aspects, but is still trained on limited angle data. And this is the one when you also imposed on the learn primal dual to make sure it's microlocally consistent, if I may. So it actually gives you quite a drastic improvement. And then you can apply it to fully sampled data also. Here's the next image. Again, 40%. Now this is the missing region. Ground truth image, much more complicated. Again, learn primal dual, limited angle, looks like crap. For example, this region here, you don't see at all. It's totally washed out. It's in the missing region, missing cone region. You can see that these features here are washed out or hard to make out. This separation here is, you don't see it. So here's when you apply the microlocal consistency on the learn primal dual one, and then you get something like that. So suddenly this becomes visible. It was totally invisible here. This slit here is what was invisible, becomes visible. It's also replicated here. So so it seems to be to force the deep neural network to not only respect the fact that you have a forward operator, but also to respect to a certain extent the canonical relation, and it seems to be beneficial. And I think I should stop here. I'm done. I'm out of time. I'm sorry for being really rushing this thing fast. So thank you for your attention.
Cool. Thanks, Ozan, for a great talk. A lot of interesting material. So if you have questions to Ozan, please unmute yourself and ask the question.
Hi, Ozan. I'm wondering how you choose the training data. I mean, that's really important for these neural net things.
Exactly. Well, this is all simulations to begin with. Second part, this training, at least these Wavefront Set Extraction parts, they required, you somehow need to know the wavefront sets, right? So this is nasty problem. So what we did here is, of course, for the ellipsoids, it's simple. They're analytically given. So you can actually compute analytically what the wavefront sets should be. So that's the easy part. When we moved on to this more brain type of thing, things become nasty. So there we were a bit lucky because Michel Unzer has a nice data set of brain phantoms where the edges are given by splines. So what we did was simply to essentially piggyback on that effort. So we took that spline. So that's why you get this blocky. Essentially, if you look at here, you see that why does this is for fully sampled data, but it still looks blocky, right? Why does it look like that? Because these networks are trained on almost essentially piecewise step functions with edges that are given by spline curves like that. So, and of course, if you can train on, the tricky part is how do you get your hands on training data when you have even more complicated images with more complicated ramp type edges and so on. That is, the whole approach requires that. So this is how we did it in this context.
Thanks.
Okay, so I have a question. Okay, so first, if you go back to the slide where you talk about the need for infinitely many measurements to recover the actual waveform set, and something about Pelly-Wiener and so on.
You mean this slide about the lack of? Oh no, sorry, wait. You mean this slide?
Yeah, okay. I mean, for all practical purposes, those lines are not really lines. They are small tubes or whatever.
Yeah.
And you have some loss of resolution, which is actually good. So you don't really have high frequencies. I mean, you don't have infinite frequencies, to be more precise.
Yeah.
You have a frequency limit, so this is actually a sampling problem. And the answer is quite simple. So if you undersample, you're in trouble. If you oversample, that's good. So there's no real need actually to go to infinity. There's no really infinity in those problems. It's
You
a
mean the whole?
semi-classical, let's put it that way. It's a semi-classical recovery of singularity. It's not really classical one, and you don't really take this parameter to be zero.
Which parameter is it?
I mean, in your case, that will be k.
You mean the band limit? You're telling me that this is a strange requirement that you look at the infinite.
Yeah, I mean, the band limit might be high, but practical problems is more or less fixed.
Yeah.
You never really go to infinity. That's my point. And
yeah. I mean, yeah.
So it's basically a counting problem. If you have the band limit, then you can tell how many measurements are enough and how many are not. Okay, second remark, when all those images that you show to us, they have more or less the same data, right? Tikhonov
Images we're talking about
yeah, with
these images.
I mean, yeah. So they have more or less the same data, right? So if you
have exactly the same data, they are recovered from the exact same data.
Tikhonov and compute the radon transform, and then invert it, you're going to get very nice shape log, which will be wrong, right?
I'm not following you. I mean,
okay, take the Tikhonov phantom and compute the X-ray transform of it.
Yes.
And invert it with your method. You're going to get the joint LPD or something like this, right?
Yes.
And that will be wrong because this is not the original.
Okay. What is the comment? I'm sorry. I'm not following.
They have more or less the same data. All those phantoms.
What do you mean by more or less? I mean, it is the same. They are getting this. They are all getting the same input. What do you mean by more or less?
No, I mean the reconstructions. If you think of them as originals, if you compute the radon transform with those reconstructions.
You're putting this as input to for forward projection. Is that what you're doing?
More or less the same. And the algorithm somehow prefers one reconstruction to the other. So there's something hidden there, maybe sparsity or something like this, right?
Yes. I mean, depends on how you regularize, but yes. I mean, this is no sparsity here. This doesn't assume sparsity. This is not sparsity here.
Yeah, whatever it is, I mean, again, in order to distinguish one of them among all of them, and they have more or less the same data, right?
But I mean, they are different estimators. I mean, this is sparsity-based philosophy. This one, and this is sparsity-based philosophy. Whereas this is essentially Bayes estimator. This is not sparsity-based. So
no, whatever it is, I mean, saying that there's some choice in that algorithm that makes them different, and basically solving the equation 0x equals 0, and then you're producing many answers. Okay, I really like this one. But they're all possible answers because they all have more or less the same data with some license.
Okay, now I hear about a third of what you're saying because it gets garbaged out. I'm sorry, I can't hear what you're saying. There's an echo going around. I don't know what's going on.
Yeah, well, okay, sorry.
I'm sorry, Plamen. I just hear a third of what you're saying.
Okay, let me repeat the stories. All those images, if you take them as input,
yes,
they have more or less the same radon transforms.
Yeah, I think, okay. If you say so, okay, go on, continue.
Okay, so if you take Tikhonov as the original,
yes,
your algorithm will produce something like joint LPD.
Which algorithm will produce joint LPD?
The joint LPD one.
If you apply the joint LPD on the data that is produced by using the Tikhonov as input, is that what you're saying?
Yes, and we're going to
okay.
Now get the picture down to the right.
Now I am understand. Now I'm getting to understand what you're saying. Okay. So you're saying that if I would put this as input instead of this guy, right? And I would generate sinogram from this one, okay? Most likely the joint will come up with this one, which would then be wrong because you had this one as input. Is that what you're saying?
Right.
Okay, okay. Well, if that's the case, I haven't done that test. That's a good test to do. I mean, if that's the case, of course, then you would say, how do you know that this is doing the right thing, right? I mean,
can you really send you a file where there will be some pattern under a limited angle, which will be absolutely invisible for all practical purposes? You basically get
of course you can. I mean, of course you can. I mean,
and there's no way you can reconstruct it, whatever you do, because it's basically zero. It looks like zero there.
Yeah. Yes, I agree. I agree. I agree. Well, it depends on the training. Yeah, okay. No, I don't have a good answer to that, apart from that saying that I would love to. It's a good question. Good comment.
Okay.
Yeah, I have a related question. I think the thing is basically you have data very close to your ground truth. So for example, for the brain, if you don't have that, you don't train on those very similar brain data, instead on other kind of data where you have different kind of wavefronts. Can you reconstruct it out?
That's a good question. I mean, put it this way, I wouldn't say, when you say you have data that's very close, for example, the shape Logan thing, these are random ellipses. So,
well, that's one thing, but that's very kind of, you have very simple curvature, curves, all these things. So it's not like very complicated shapes.
I agree. It's not, I mean, life is much worse than that. The brain phantom, or let's call it the brain phantom. Sure, if you train it deliberately on, let's say, an inappropriate training data set, you will definitely get into problems. I fully agree with you. To what extent we have done stress tests on this is still work in progress. Let me first flash that. It's quite laborsome to come up with these training sets. As Margaret was asking, we need to, extract out the wavefront sets for the training purposes. So I would expect that if you train it on, I don't have a good answer to how bad your training data can be for you to have something decent, right? I can answer that better when it comes to the purely reconstruction part, leaving out any wavefront sets. There is actually surprisingly robust. But with the wavefront set, I have no clue. That I don't know.
So for example, you create all kind of different shapes with different curvature things, and you generate the data according to that. If you learn from those, can you create for the brain one?
I mean, it's a good question. I mean, it's a local concept, right? The wavefront set. So you don't need to. I mean,
it's a local concept, so you can train in all kinds of. You can
train on a huge number of training data sets, right? It's essentially.
Yeah. So just the geometry, of different geometry of the wavefront. You train on big. You synthetically generate all possible these kind of things. You train them. Can you generate the brain?
Well, in principle, yes, but you need to be careful here because you need to be clear. I mean, you need to also be careful how you design your neural network architecture. And you need to be careful. There are many things that you need to think about here. So it's not as easy in that sense.
But so my question is whether it's really learning how to extract or it's kind of interpolating between nearby points to get that front.
Well, I mean, I would then bounce the question back to say, really, what's the difference? I mean, in that sense, you're interpolating by statistical learning. So in some sense, you are filling out the missing region, as Clement was saying. I mean, mathematically, there is a missing data there, right? So you are supposed to fill it out by some principle.
But this extrapolation in a very different space. One is in image space, very huge. The other one is in a very small space where it's just the different orientation, different location. Yes. If you learn the huge space, that's going to be very inefficient. If you really learn on the intrinsic characterization space, then you don't need that much data. You can be more efficient.
Yeah. In principle, what you're saying is correct. In principle, I mean, we put it this way: we haven't done many of these questions about what is the characteristics of your training data, how close does it has to be to your, let's say, your real images. These are experiments that I don't have any theoretical answers to any of these things. I think one needs to do some experiments first to begin with, to gain some feeling for this. And so essentially I would foresee like this, that when you do domain adaptation for the neural networks, you can lessen the amount of training data you need. That's very clear. So when I did the long time ago one, we accounted for the forward up. What we're trying to here is to also enforce some kind of consistency in the microlocals. Okay, that's what we're trying to do, and I'm sure this could be done in many different ways. This is one attempt at doing it. Yeah, I don't know. It's a nonsensical answer, perhaps, but.
Thank you. Yeah, this is just, I have very little experience. Just want to see when you're training whether you really learn in the small space where we have good characterization, or you learn from the big space where it's really data point interpolation rather than feature-based interpolations.
I think it's, honestly speaking, I think it's a mixture of both, because we are doing the joint training of the reconstruction and
I agree. You have.
So it's a kind of a mixture of both. It's not so easy to characterize which estimator you're actually working with at the end of the day. Yeah.
Yeah. Thank you.
I have a quick question. Thanks for the talk. So you said 10 to the 16 parameter is out of reach. So you know what the order of magnitude typically is for training neural nets?
Which that's a very super generic question. In what context?
Oh yeah. Well, I guess in your simulations, then what order of magnitude do you end up with?
I mean, when we do just the to give you a feeling for what happens if you take the reconstruction problem only, forget about these wavefront sets and everything like that. That's pure reconstruction problem, and you would if you would try to treat it, forget about the forward operator and just go brutally data driven on this problem, then at least you would need about 50,000 pairs of images of ground truth and corresponding sinogram, give or take, to have a chance of getting something near the quality that we are getting with about 2,000 images when we embed the forward operator in there. When it comes to number of parameters, if you do it fully data driven in the 2D setting, you typically have about 10 to the power 7 parameters in the network that you need to learn. When you do it with this when you do it with the architecture that's adapted to the inverse problem, in the sense that it embeds the forward operator and so on, you're down to about 250,000 parameters, which is of course much, much easier to train. So these are the numbers I have back of my head, right? And of course, is there a theory that tells you how much you can get away with? Brutally answer right now is no. There is no theory that I know about. Would love to see anything like that. There is no sampling theory in that sense. How many training data points do I need to get certain accuracy and so on? All this is open questions.
Thank you.
Hi, I have a quick background question. Why do you use shearlet representation versus wavelet, for example?
Well, quick answer, I was working with Gita. Second quick answer is that, you know, we already had, I mean, this a lot of software engineering goes into this, right? And she already had a lot of, you know, bindings for the software libraries and so on. So there's, it seemed to be a well-designed software package for doing the computing the shearlet representations and so on. So it was guided very much by pragmatic issues in the very beginning. But I cannot, yeah, that is my quick answer. Okay.
Well, are there any more questions for Ozan, or otherwise I suggest we thank the speaker once again for a great talk. Thanks a lot. It's excellent.
And